Hello students, welcome back. In the previous videos, we went through some long and tedious examples. 2 on inverse matrices and 1 on systems of linear equations. The reason they were so bad was because we had to rely upon the elementary row operations. We had to apply a long sequence of elementary row operations to each problem. If you look at each individual elementary row operation, then it's easy. But if you have to repeat it so many times, at some points, you're going to make a mistake. You will make a mistake and get frustrated. But that can't be helped, and I'll try to be as generous as possible when grading. But then again, finally, we are done with those, and let's move on to a little bit more theoretical topic. Fair warning. This is a bit theoretical topic, going maybe a bit too much into the philosophy of pure mathematics. So if you're not that into it, then you may skip this video. If you do like it, or if you want to explore it, what's it like, you're welcome to stay and let's talk about it. Let's begin with the proper definition of the inverse matrix. This is a description we use, but there's a problem. We are using the inverse matrix, the term and its notation, before even defining the inverse matrix. That's problematic. So how do you make it right? And that's where this kind of definition is coming into play. We define the invertibility first, and then define the inverse matrix. Let's go. An n by n matrix A is said to be invertible if there is an n by n matrix B such that A times B is equal to B times A, and that is equal to I, the identity matrix. So if such matrix B exists, then A is invertible and all is fine. And then, if it is invertible, then can we now define the inverse matrix? Well, there's a bit of a problem still. The best candidate for this inverse is, of course, this matrix B that satisfies this, but here's a problem. How many are there? Are there 5? Are there 17? Or maybe infinitely many, in which case, of course, everything is moot? Or, as we want, there is one and only one for given A, so that we can call it the inverse matrix. Of course, that's the case. That's why we call it the inverse matrix. But that's something we'll have to prove. As a matter of fact, in pure mathematics, whenever you define something, always you'll have to establish whether that is well defined. Basically, you have to check 2 things. Number 1, existence. Number 2, uniqueness. Existence in this case is okay because we established the concept invertibility. So if it is invertible, then yes, inverse matrix exists. This kind of matrix exists. But if A is not invertible, then inverse doesn't exist, and we'll just move on. So in this particular case, I don't have to worry about the existence. The uniqueness, on the other hand, yes, we have to establish it, and let's talk about it. It goes like this. What if there is another matrix C that satisfies the same condition? Basically, I'm talking about this here. Let's read through. Let's suppose there are matrices B and C. Both of them are n by n matrices, such that A times B is equal to B times A, and that is equal to I, the identity, the same as before. And also, AC is equal to CA, and that's equal to I, exactly the same as previous, except that we are doing matrix C. Basically, if we have 2 inverses, then what? Then these 2 matrices have to be the same, which means there cannot be 2 different inverses. They have to be the same. In other words, the inverse is unique for a given matrix A. Consequently, we can define it as the inverse matrix, and we can give appropriate notation. We're going to notate it as A to the negative first power kind of thing and call it A inverse. Of course, we have to prove it to make sense out of everything. The proof is, as a matter of fact, pretty simple. Start from B, and then let's apply B times I. Yes, that's correct, because I is identity. And then what is I? It's AC, because we assumed this. But then again, we can apply the associative law. So we can group BA first, and then apply this. BA is equal to I. And I is identity, so we get C. The consequence, B is equal to C. So these two are same matrices. As a matter of fact, these are not two. We are talking about the same matrix. So there's only one inverse, and we're going to call it the inverse matrix, and then denote it A inverse. So finally, the inverse matrix is well defined. And then let's take just one more step. Look at this invertibility condition. We have A times B is equal to I, also B times A is equal to I. The definition required both. But then again, when we prove the inverse, we didn't actually prove both. We just established one and then just moved on, as if it is okay. The reason we can do that is because it's okay, really. If A and B are n by n matrices, then AB equals to I means BA equals to I, and vice versa. So when AB is equal to I, then automatically BA is equal to I, and vice versa. So we don't really have to check both. The problem is, this proof is, well, I'm not going to say this is beyond the scope of this course, but at this moment it's impossible. We have to go through some rigorous detail toward the end of chapter 5. Toward the end of chapter 4. Yes, and toward the end of chapter 4, we may be able to do it. Chapter 4 of our textbook, not module 4. Is it chapter 5? Oh, excuse me. I think it's chapter 4. Oh, never mind. My point is, we cannot do it now. And also one more thing. It's true for finite dimensional matrices, n by n, but in some other cases, maybe not. And we may have left inverse and right inverse, and basically we can open a floodgate out of it. Okay, so much for inverse matrices. And the next topic, again, quite theoretical topic, is section 4, linear combinations. Basically, this is a preview of what's to come. We're going to come back and reintroduce this concept, linear combinations, with proper definition in chapter 3 of our textbook, vector spaces. So at this moment, please consider it as a preview of what's to come, or we are taking a glimpse of what we are going to do a little bit later. And of course, we are going to confine ourselves only to matrices, not to arbitrary vectors. Let's begin. Let's begin with a matrix A, an m by n matrix, and let's consider its column vectors. Capital A1, capital A2, all the way to capital AN respectively. And please note that I use color coding so that you can see things better. By the way, if I use subscript, then that usually means the row vector, and if it is capital and subscript, really it usually is the row vector. If it is lowercase font and then subscript, it can be still something else. So if I use subscript, I'm talking about horizontal, but in this case we are looking at the column vectors. Okay, so much for the notation issue, and let's go over to the computation. Let's go to the main computation. Let's consider this, A times X, where A is an m by n matrix and X is an n-dimensional column vector, or n by 1 matrix. How to calculate this? Basically what we do is to take the scalar product of each row and the only column. So what we multiply? First entry times first entry, blue. Second entry times second entry, red. Third entry times third entry, and so on and so forth, all the way up to last entry times last entry, green, and then adding them all up. And that's being repeated m times through all these rows. And that's what we see over here. Does it make sense? I hope the color coding helps. Okay, once we got to this, the next step is easy. Simply decompose all those columns, blue, red, dot, 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 green, separately. And then if you look at each column vector, you'll see a common factor that can be factored out. I factored x1 out of here as a scalar multiplication, and x2 out of there from here, and then finally xn out of here as a scalar multiplication. In the end, this is what we got. Ax is equal to x1 times a1 plus x2 times a2 dot 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 plus xn times an. Here is a summary version of it. So Ax is equal to x1a1 plus x2a2 plus all the way up to plus xnan. And if you use summation notation with sigma, you can express it in even simpler form like this. And this kind of expression is called the linear combination, the title of this subsection. Now, how do we use this linear combination? One of more typical use is linear independence. Let's take a linear combination, and let's suppose linear combination is equal to 0. And what does that mean? If you can have 0 only when all the coefficients are 0, x1, x2, x3, all the way up to xn are all 0, then we'll say these column vectors a1, a2, all the way up to an are linearly independent. Now what if we don't have to have all 0? There is a nice sequence, x1, x2, all the way to xn, not all of them 0, maybe just 2 of them 0, maybe 17 of them 0, maybe all of them non-zero, whatever. At least one non-zero, that much is necessary. Yet still, x1a1 plus x2a2 and so on, plus xn and an is equal to 0, or simply the linear combination is equal to 0. In that case, we'll say these column vectors are linearly dependent. So linear combination is equal to 0, implying all coefficients are 0, versus no, not necessarily. There is a sequence of coefficients x1 through xn, not all of them 0, but still the linear combination is 0. In the latter case, we'll say a1 through an are linearly dependent. These will turn out to be a very important concept in, let's see, chapter 3 and 4 of our textbook, and comes back again in chapter 7. In short, we are talking about something important here. Now, let's get some closure out of it, and that's this one. The linear dependence and linear independence are related to having trivial solution only or non-trivial solutions possible. So what does this one mean? Ax is equal to 0, meaning only zeros are solution, so only trivial solution exists. That's what linearly independent means. So linearly independent means only trivial solution, no non-trivial solution. Look at this one on the other hand. So Ax is equal to 0, but x1, x2, x3, all the way to xn need not be all 0. That means it has a non-trivial solution. one non-trivial solution, consequently infinitely many, as a matter of fact, because of the homogeneity. We can multiply by any constant and make more, and then there may be still more. And those kind of situation, we call it linearly dependent. And that's how things are related. We can consider linear combinations and matrix multiplication in the same boat, and then consider linearly dependence, linear independence, as the concepts associated to possible trivial solution or no non-trivial solution. And that's about it, and we are going to end this chapter right here.